us. Coming here.
You from Munich?
I'm from Munich, yeah. So I'm based in Munich. I work remotely.
Yeah. And I'm Linda. I'm from New York. So it's been not my first time in Israel. I was here for Sukkot, but definitely first time with Anyscale here in Israel, and very excited about that. How many of you have heard of Anyscale? Cool. Well, this is a Ray meetup. How many of you have heard of Ray? Awesome. How many of you have tried Ray? Awesome. Okay, okay. What are some workloads you guys are working on right now? Feel free to shout it out. Or like use cases. Data, training, where's the inference? Serving, okay. Awesome. What else? Anyone training, inference? Training? Post-training, reinforcement learning? Nice. Okay, we're going to talk about all of that. Before we get into it, very important question. Do you like popcorn? Yay, okay. Do you like movies? Yes, except I can't give you popcorn, but I could give you an analogy with popcorn. So I have no idea if this sound is going to work, but I was thinking, I know that with analogies, really like analogies, and popcorn is a great analogy for online inference versus batch inference. So maybe we'll learn about it, and you probably maybe know the difference, but if not, it also reiterates. Let's see if the volume even works, and I'm sorry to show a video of myself. I would have brought a microwave and actually shown it to you, but we don't want that. I know, I know, now I don't have an excuse. Okay, so let's see if this works. Oh, I don't think it works. Does it work? I'll have to do a voiceover. Okay, so when processing data, there are two main ways to run inference. Online inference is real time, like popping one kernel the moment someone's hungry, which is optimizing for latency, right? Like chatbots. But batch inference is offline. You wait a little longer, but you process everything at once, which you can power a big job. Sorry, I'm reading my own captions. Really weird, but it's okay. But the point is, when I was eating popcorn, I realized that it really is a great analogy, because the thing is that the GPUs are your microwave, and your CPU are your kernels, and you need to prep the data, okay? Like you have to put the butter, whatever. And so if you're prepping the kernels, and your GPU is sitting idle in your microwave, what's the problem? If it costs you money to run it. It's costing you money to run it, right? Okay, so how to utilize it? You have to have the processing happening with the GPU, and it needs to coordinate. So this is kind of the concept of batch inference. I don't know if this helps. Did that help? Did we understand? Okay, so who wants to eat one kernel? Okay, there we go. And if it doesn't help, thank you for making me feel better. Wait, your microwave.
You want more than one popcorn, yeah? We want the full.
Can you tell us, Chet? All right, so now we're going to get into the actual talk, so you know who. Okay, we introduced ourselves, so that's great. Okay, so batch inference. What is batch inference? Today we're going to be talking specifically about batch inference. Oh, the previous slide. What's the previous slide? Us. Oh, thank you. We got the social media. There we go. Look, I like the thinking. So batch inference, right, is the process of generating predictions on large sets of inputs at once using a trained ML model. So, right, we like popcorn, think your microwave, right? But we do want it to be a large machine that also processes the data and the popcorn at the same time, so we're not having your GPU idle. All right, so as far as batch inference goes, we are seeing a lot of complexity in batch inference. What are some of the problems? Maybe you can see it on the screen, but what are some of the problems? So some of the problems I'll tell you, we have a lot of Python processing, and a lot of it was not built to be Python native. Our ML workloads and AI workloads are Python native, but you have a lot of other things that are Python native, and if you're trying to distribute, if you're doing some distributed training or inference with Spark or other things like that for unstructured data, you might get into some lack of optimization there, and you might be paying more for than what you need, right? The other thing we're seeing is unstructured data, right? So you're seeing a lot of video, PDFs, multi-modal type data, and then we're also seeing a mix of CPU and GPU. What was the analogy in the popcorn of CPU and GPU? The big machine, right? You want to be able to process both and utilize, and this is a dance. And some of us want to just focus on being machine learning engineers, or just building the stuff and not with being distributed computing experts. So a lot of it is going to be, we talked about VLLM, right? The topic here is efficient VLLM. VLLM, and we're going to get into it, I'm kind of jumping the gun here, but VLLM and Ray work really well together. Ray actually is under the hood of VLLM, And we'll talk about the differences in a second. But in general, we have to scale batch inference. And usually when you scale batch inference, you have input data, read, pre-process, embed, upsert, and output. Now this is obviously a small example, but what you see here, CPUs and GPUs and a lot of coordination, right? And you want that, and obviously it gets more complicated because they also might communicate with each other. So that's just if you're a visual learner. All right, so some of the challenges we have with batch inference is compute. We talked about this a bit with the heterogeneous clusters, scaling it, and with also observability, reliability. You also want to have checkpoint, fault tolerance, all that fun stuff. And of course, we have drift in production, all these other things, your downtime. I'm not going to bore you with reading all this. You get my point. All right, so this is a Ray meetup, so I'm going to give you the quick spiel of what Ray is, so I level set, and then we're going to get into, I personally think hands-on learning is the best way to learn, yeah? Coding, a little bit. So we have actually a demo that you can take. I'll give you a QR code. We'll walk through it, so you'll get an analogy. You don't have to do it here, but I think it will show you kind of the process of how you can use VLLM with Ray to distribute compute. And so I first need to explain to you what Ray is, so here's what Ray is. So Ray is an open source, Python native distributed computing engine. With Ray, you have Ray Core, which is you can take any Python function, pretty much distribute it from your computer to multiple machines, all just a library, right? It can sit on any hardware of your choice, AWS, GCP, Azure, anywhere you run Kubernetes, on-prem, whatever you want to connect to,
ABS.
Yeah, Jinx, and which we'll be speaking very soon. We also have a fun announcement, Anyscale new business. So, and then on top of that, we have libraries. So Ray does not just, we're here with the inference, we're running with inference here today, but Ray works across your ML pipeline. So everything from data, training, serving, you have RLib, a lot of different libraries which are built and have a lot of native integration with VLLM, Hugging Face. So we have functionality within the libraries that does a lot for you. Okay, so you could focus on building and not be a distributed computing expert. All right, so this is all open source. Okay, this came from the Rise Lab, Berkeley, same lab as Spark, if you're familiar. And Anyscale is just a company around that, but Ray is open source, free to install, free to use. All right, so today we are going to just talk about, and I'm very bad at pressing, sorry, I have a clicker, but you know, jet lag. Ray data, we're only going to talk about Ray data, PyTorch, and VLLM today. There's a lot more to Ray, but this is what we're going to focus on today. And this is pretty short, so it's not going to be that long. Essentially, the demo I'm going to show you in a moment shows you, I like visually showing what the architecture will be. This is just a simple example. Let's say you have a CSV file with 2 million customer records, and you want to actually change it to be able to change the formatting, right? You have 2 million customer records on a CSV, and you store it on an S3 bucket, and let's say I want to use a model. Here I'm going to use Llama 3.18 billion parameters, and then I need to post-process and put it back in cloud storage. So here, the thing is, from a computing standpoint, is I need to read and pre-process it with CPU, and then I need to actually use GPU, right? And then I need to also post-process with CPU again, right? There's a dance. Now, here's the thing. Large language models are large. And so, when I'm also doing batching, I'm not just batching the whole process here, I have to also batch within the model, which is why you use VLLM, okay? So think of VLLM as within the box. You need to actually optimize within the box. And think of Ray as optimizing across. So your CPUs and GPUs are all working in coordination together across. Okay, so you're parallelizing your data, data processing. You're parallelizing your training. So that's pretty much across. And VLLM is in the box. I just say in the box, across the box. VLLM uses Ray under the hood as well. So they kind of have very strong integration. And there's a lot of, in the library you'll see in a moment, Ray data, which is the library we're talking about today, has wrappers around it that pretty much help you run VLLM efficiently. So it just does all that coordination for you so you can focus on building what you want to build. All right, so I'm babbling here, but this is the QR code. I'm going to show you also the demo itself because I like doing a quick walkthrough. We just saw we're going to pre-process, post-process, and all that functionality. We have a notebook that actually you can walk through it. It's free to use. It's free to, there's also Anyscale itself you're going to see I'm going to put it in I'm going to spin it up in the console of Anyscale. You can run it anywhere you want. You do not have to run it on Anyscale. Anyscale gives you $100 of free credits without a credit card. You put the email, and you can actually spin it up and play around with GPUs on our without putting your own cloud on it. So it's kind of fun if you want to like play around with compute. You can even do fractional compute. You can play around with it. It's a good way to learn. It's free. You don't have to put it with a credit card, but you could also take the notebook and put it locally. I mean, you don't have to use Anyscale. I'm going to show it there, but anyway. So where am I? Okay. So now let's go to the hands-on lab. So here, this is what it looks like when you go on the page. Let me know if the QR code did not work for you. And what did we say? We have to prepare the data. So what I want, I'm going to focus only on a couple of things, but this is pretty much there's step 1, 2, 3, 4. Four steps. That's what we're going to go through. So step 1, we're going to prepare a data set. Where I want you to see, here I'm importing Ray, right? Is it big enough? Is it okay? Oh, sorry. Hold on. I'm hitting my mouth with this. Okay. Here I'm importing Ray, and I have an S3 bucket. I'm storing my data, my 2 million rows on this S3 bucket. Remember, that's my use case right here. And here I can say ray.data.read CSV. It could be a CSV, it could be a parquet, it could be any format. Here it's CSV, and it will actually parallelize it for me, right? So here I go ray.data, whatever, and it parallelizes for me. I don't need to think. It was how many CPUs I have. I define it. That's it. For purposes of this notebook, we're limiting the rows because we want this to run today efficiently. And then here, this is where I want you to look at. Here's where you kind of define the kind of like the batch sizing here. Here we're putting 128. You want to play around with it, obviously, for latency and throughput. Ray is open source and has a built-in dashboard that you could also spin up, so you could see and kind of play with it on the throughput and latency. Essentially, this doesn't do anything yet. You're just preparing the data. So what did we do? We took 2 million records. We said we're only using X, whatever, like 100,000 rows. We said we want to batch the partitions to be 128, and we're reading from this S3 bucket. With me? Yes. What are we reading from? Yofi. Next. I know it's late. Step 2. What are we doing? This is the part that's interesting. Here, Ray actually has a built-in, and I'll show you a slide about this after, but Ray has a built-in functionality, ray.data.llm, and here, all the parts that VLLM you would need to configure, you just need to put this config, and it will spin up also VLLM with Ray for you and orchestrate it for you. So it's kind of like it has a built-in library, so you don't have to start defining, if I have one GPU, if I have more than one GPU, it will check if you have one GPU, doesn't matter. If you have more than one GPU, it will run certain things, and it will do certain things with VLLM. What I want you to look at is the batch size. Obviously, this is a part that you have to also sometimes play around with. But this is for you to know that it's in the library. That's all you have to do. And again, it would be really painful when you start doing large size data with multiple machines and you start writing this out just with VLLM. If you're just one machine, okay. If you're multiple machines, it's going to get painful. So unless you want to sit there doing infrastructure all day. All right. So although I'm a DevOps engineer by trade, and of course we were just not appreciated, but love for the DevOps. Hug ups. Okay. Anyway, so now nothing ran yet, right? All I'm doing is defining. Great, I defined my VLLM config here. Now I'm defining the pre-process and post-process. Okay, pre-process, post-process, and then I'm not going to bore you with this. And then here I bring my pre-process, post-process, and in a way, all I'm doing is using Python to distribute across multiple machines. I say here let's see, where did I put it? Here, let's look for it because I forgot to say this. I'm defining pretty much how many GPUs, and I lost where I am. And then here's where I'm actually running it. So the only thing that runs it is this, .materialize.take. That's how it's actually running. Till then, I was just prepping. And so I'm not gonna be able to probably run through the whole thing, but if you wanna see how it actually plays in the notebook, I ran this before right here. You can see here, it loaded the data set. We defined, here, let me see, I'll run this. And it's within the notebook. You could do this here just for you to see. I defined the pre-process and post-process functions, right? And if I look back at this, all I'm doing, right, is this. I'm defining the pre-process function. I'm defining the post-process function. I said this, and there we go. We're pretty much just the architecture we're building, right? I'm just going to go quickly to here, because I want to show you this. So Ray data has functionality specifically for large language models. So just for you to see, you have the continuous batching, which Asaf gave a great explanation on. Tokenization, detokenization, disaggregation, load balancing, and all these other features, just for you to see like what's built in within Ray data. And it's a library on top of Ray Core. It is open source, so if you need to use Ray Core and you have very specific use cases that are not covered for some reason, you could also do that. And then I'm going to pass it over to Carl to say a bit more about Ray, Anyscale, and hopefully the mic works.
Yeah, for sure. Yeah, so I mean, some of you know Ray. Some of you maybe have experienced some challenges when distributing workloads. And yeah, so was it for us when we developed Ray. And basically what we offer from Anyscale, right? I'm at Anyscale, is a whole platform to deal with these kinds of issues, right? Like once you start a new project, right? You want to scale from a single node to a multi-node setup, then you want to run into production, then you need to scale your cluster, multiple regions come into play. Like all of this, it's handled in Anyscale, don't worry. And I'm gonna show you a bit what we're up to here, yeah? So basically, what we focus on is we focus on being the best place to run Ray, basically. So everything you do is fully compatible with your open source Ray, so there's no login, no bullshit, it's all clean. But what we offer is we have a faster IDE for you to develop your stuff, to debug, you have flame traces, things like this. Observability, it's persistent, you can share it across. We have RBAC, all of this is implemented. We do a lot of stuff around reliability, of course, because that's very important once you go in production, and if you scale across GPUs. And yeah, we have a bunch of functionalities as well, yeah, for efficiency in the end. I'm gonna go fast. Yeah, so if we talk about reliability, there were a few announcements that we made at our recent Ray Summit, beginning this month in San Francisco. So we have now dynamic memory management. So if you see that certain nodes go very high on memory or very low, we vertical resize the node. We have mid-epoch resumption. So if you're training, we can actually catch errors and restart exactly where you left off. So if your training fails, we keep track of the step at every state. And especially if we're talking LLM, you know that an epoch can be quite expensive running it on several GPUs. We do have elastic training. That is especially interesting if you're running large clusters or if you're running on spot. So you could, for example, do a scenario where you have 256 GPUs training something or doing a batch inference job, whatever. And you wanna make sure that this job runs on that much amount of GPUs. Then we make sure that within the tolerance band, we keep your job running using our reliability features. And if you fall below that, we'll help you search for new resources and pause the job and can then, of course, efficiently resume. And we have a bunch of functionality around GPU profiling, growing amount of tools. You can also check them out. If you go through the tutorial in Anyscale, you can also go to all these profiling tools and stuff like this. Really cool to see. Yeah. So two things I want to show, and then you're done. Then you can go to the beers. Yeah. So one thing that we recently announced, it's now in beta, is our multi-resource cloud. So imagine you wanna do such a batch inference. You say you need one H104 or whatever, right? And you just need this resource, and you search across clouds. We can help you with this. So you hook up your different clouds and regions and deployments that you have, maybe some on Kubernetes, some on VM, into our system. And Anyscale decides for you what's the most efficient way to schedule stuff right now and puts it all together for a cluster. So you can, in the end, then run your job there, and do not need to worry about this, right? Where I'm from in Germany, it's a big problem. GPU availability and stuff like this, it's still not solved. So there we see a high demand from. And then, of course, we have something really cool that I want to show you. Is the global resource scheduler. So yeah, some of you might have seen this already. Imagine you're doing something that like the big AI houses are doing, big reservations of resources, can be CPU, can be GPU. GPUs are obviously much more costly, so you want to make sure you utilize them very nicely. And let's say you deploy something, you're running a few jobs on schedule, and you need to make sure that, for example, your inference runs always get through with high priority, high latency, low latency. And then you have a bunch of other stuff that you want to run, like a training that you don't really care about, right? But you just want to run it with all that capacity that's left off, right? But what people usually do, what we observe, is that you would then assign like different quotas, right? So you say like, okay, we do this big block for inference because our inference can scale up to, in this case, 20 GPUs, right? And then we still have a bit of availability, so we're gonna go on training jobs with that. But now, I made this block here like this, that you see, okay, at this current load, actually your inference only uses part of its reservation, right? So there's a certain amount of GPUs that's unused. And that's something this global resource scheduler takes care of. So if you consider everything, you can set it up in such a manner that basically we put these jobs that you prioritize onto this GPU fleet, and we'll size exactly the amount of GPUs on these high priority things like inference to the demand, right? So here we have a low demand, and then we go through it, here going a bit up, right? Preempting this training job 1, let's say it's very low priority, you don't like the developer, whatever, right? You don't give it priority, don't get GPUs, whatever. We can still help you to find GPUs across regions, things like this, right? So that's implemented in the platform, but we make sure that the inference runs smoothly. And then, of course, right, you can take it all the way, and then once you see a lower demand again, we start putting back the jobs on, and that also plays very nicely with these reliability features that we have, because then we can basically continue where we left off, right? So these are some of the things we are up to. There's much more, but we don't have enough time to tell you all of it. If you want to see like where does Ray sit in the stack, I can also explain a bit about this. So imagine you have your AI workload. You can basically do a bunch of different things to realize it, right? To implement stuff. And I will go about this briefly. So you have somewhere you compute substrates, GPUs, CPUs, and of course storage. It's not outlined there, but also very important. And then you build a stack on top. And what we observe right now is a new stack forming that's basically based on PyTorch, VLLM, Ray, and Kubernetes. So that's what we call the Park stack. PyTorch, AI, Ray, Kubernetes. That's what a lot of people are doing out in the open source. It seems to be a really winning system. VLLM is actually coming from the same lab as Ray. Same as Spark, same founders. VLLM guys are often in our office in San Francisco as well, so we are very close with them. That's also why we highlight it here, of course, and it's really well integrated within Ray. If you want to learn more about the differentiation between Ray and Spark, you can also ask our colleague back there, Ollie. He was quite a while at Databricks when it was still very small.
Ray just joined the Linux Foundation, actually, and so they all sit under the PyTorch Foundation right now. So PyTorch, VLLM, Ray, Kubernetes. So that happened recently. So we're really excited about that. There's also, just so you know, there's an Anyscale startup program if you want credits and stuff like that, that you could apply to as well for support as well. And I know Israel, Startup Hub. So definitely apply. Definitely if you want some free compute and support, why not? We have a startup program. Feel free to take the QR code. Do you need the QR code again for the hands-on lab? Or do you have it if whoever wanted it? You're good? Awesome. We're so happy to be here. Thank you so much for having us here. Thank you to AI21 Labs for hosting.